Hello, my name is Craig Stevens and I'm the chair of the Department of Radiation Oncology here at Beaumont Health. I'd like to welcome you today as a PT-COG member to the virtual tour of our Proton Center here in Royal Oak, Michigan. So we wish that you could have been present in our center today to experience it personally. Unfortunately, COVID-19 has kept us in a virtual format and limited our ability to have visitors. And so we provide to you today a virtual tour of our center. This video will be broken up into several parts. The first will be a tour of the center so that you can see some of the wonderful amenities that we've built into the program. We'll then also talk about the ProteusOne workflow so that you can understand some of the nuances and differences between a single room center and a multi-room center. And finally, we'll talk about some exciting new developments in proton therapy, which we call SpArc, or rotational protons. This has huge advantages in terms of patient throughput, dose delivery, and conformality. So again, welcome to our center and enjoy the tour. So Beaumont's proton journey actually started back in 2008, but fell through due to the financial crisis at that time. We'd initially started with a vision for a 5-room center, but it was restarted in 2013 with a single room proton solution. We sent out an RFP for a proton vendor to many different vendors, and this was won by IBA. The RFP process was actually critical to our success because we were sure of what we were getting. The CON Commission in Michigan had very tight controls placed on us with regard to completion of the project, such that if we didn't hit certain milestones, they could potentially remove our CON. So we were very, very conscious, not only that we would get a great center, but that we would get it on time. We broke ground in 2015, and our first patient was treated in June of 2017. So our project started in the winter. As you can see, we have robust winters in Michigan. And in fact, it delayed our center's construction start date by almost a month. We have 12-foot thick steel reinforced concrete walls in the vault area, which was essential for our shielding calculations. We then built the center around the vault, as you can see, with the clinic space for radiation oncology on the first floor and pediatric oncology on the second floor, because we wanted them to be closest to our most vulnerable patients. As you'll see in a second, there's a very large crane, which will be dropping the gantry portion of the machine into the cap. There's the largest crane in Michigan. And that was able to complete our project on time and on budget. So here is our 227,000-pound gantry being dropped into the vault of our center using the largest crane available in Michigan. In fact, there was another crane that was there to put the ballast on that crane. That's how big it was. And here is a very trusting person standing underneath the gantry, setting it into place in our center. So we treated the first patient in Michigan with proton therapy on June 28th of 2017, meeting all of our CON requirements. One of the things that's different about proton therapy versus a more standard radiation treatment approach is that the way that you commission the center is actually dependent on the type of disease that you're treating. We started with CNS commissioning. We then moved to tumors with a stable soft tissue component, such as sarcomas and prostates. We then moved to tumors that don't necessarily have a stable soft tissue component, such as immobile lung cancers, chest wall tumors, left-sided breast cancers, and head and neck cancers. We then added anesthesia for our pediatric patients. We then added mobile tumors, and we actually have yet to be able to treat eyes on this machine. And so remember, the center opened in June with our ability to treat central nervous system tumors. A month later, we were able to treat sarcomas and prostates and other stable tumors. In August, we had lung cancers commissioned. In September, chest wall and breast cancers. In October, we had head and neck cancers ready to go. In November, we started anesthesia with our pediatric populations. We began treating mobile tumors in December, though some tumors still unfortunately fail our test if they move too much. And as I mentioned before, eyes we haven't yet finished. So in order to understand our eventual metrics, you need to understand a little bit about Beaumont Cancer Center. So Beaumont Health has about 11,000 new cancer patients a year treated at over 8 hospitals. We have 35,000 employees and 6,000 physicians within Southeast Michigan. We have 19 radiation oncologists at 3 centers. 2 of those centers have 3 LINACs. At Royal Oak, we have 4 LINACs, a Gamma Knife, and our Proton Center. So it's a fairly large system. So what effect did putting in our Proton Center have? And please see our presentation at Astro this year. But what we saw was an 11% increase in photon starts across the health system. There's only 4% increase at Royal Oak because I think some of that increase actually just went to the Proton Center. We doubled our brachytherapy volumes and we doubled our pediatric volumes. This shows a distribution of new starts through March of 2021. And again, year-to-date new starts since then. And as you can see, we're on pace to treat about 200 patients a year. This is not a big prostate machine. As you can see, a lot of it is brain tumors. This is mostly pediatrics. Head and neck cancers have a large place. Lung cancers have a modest place. Prostate and breast cancers also have a small place. Interestingly, prostate, lung, and breast and sarcomas are all about the same size. In summary, we were able to complete the design and construction of our single room center on time. We commissioned multiple disease sites in a thoughtful, stepwise way and treated the first proton patient in Michigan. We also developed a robust nurse navigation model that you'll hear a little bit more about. We enhanced our cancer program significantly by placing the center at Royal Oak. As you will also see, we developed a very robust proton research and development program with rotational protons, which we'll be discussing in much more detail later. So again, thank you for your attention.
Welcome to Beaumont Proton Therapy Center. So the new building attached to our existing Proton Therapy Center. This is our lobby. We have a new reception area. Wide spacing that was advantageous for COVID. This is our lead therapist, Faith. Here's our nurses station, and adjacent we have 2 anesthesia bays, which is convenient for treating our multiple pediatric patients. And private changing rooms right down the hall from our gantry. And here we have an ambient light and sound center to make a soothing atmosphere for the patients with animations, music, and light. This is our Beaumont Proton Therapy Center gantry with the ProteusOne. And now we'll look at a specific workflow for a ProteusOne treatment. Here we're going to show an example of treating a simple brain case. An open gantry creates a calming environment for our therapist to operate, and our patients, especially pediatrics, to be calm in an open atmosphere. It also enables anesthesia equipment to easily be placed without clutter in an enclosed environment. We have an in-room cone beam CT with a large field of view. Here we have to the right an X-ray booth for in-room imaging for the therapist. We have a remote station with connectivity between the imaging and treatment gantry. We use RayStation and Mosaic integrated to our ProteusOne. Here we see the acquisition of a cone beam CT. With in-room cone beam CT allows us for quick image acquisition with a large field of view, which does not delay patient setup. Here we're looking at auto registration of the planning CT scan with the cone beam CT for fast alignment. Here we see auto registration of the shifts with no need for manual entry. Again, through an integrated imaging, rotation, and treatment system, we're able to quickly shift to the next treatment position. And with an open room, you're able to treat vertex fields easily and instantaneously take oblique images to verify position at different couch angles. Again, we see alignment of shifts and deployment of the range shifter. With again, a quick treatment field, and the treatment is done. For a 2-field brain case, the alignment, treatment, patient on-off table takes less than 15 minutes.
It's my great pleasure to be here and introduce the proton therapy to the audience here, and also introduce some of the technical breakthrough that we are happening recently in the Beaumont Proton Center. So what is proton therapy? So by its means, proton therapy is rotate the gantry and the couch in a continuous movement while it radiates a proton spot. So for example, like the picture on your right side, so this is a lung treatment with a proton with hundreds control points. So the goal of the proton therapy is to make the particle therapy more efficient, more robust, and better dose conformality. But however, there is challenges. So for example, the gantry is 100 tons. So ProteusOne is almost 100 tons and Proteus Plus is more than 200 tons. To rotate this gantry smoothly while it radiates the spot in a sub-millimeter accuracy is a great challenge, engineer challenge. Through the 6 years the planning, so we are able to publish about 11 peer-reviewed papers and 30 conference abstracts. So the ProteusOne projects including 3 phases. So the first phase is introduce the concept, which happens in 2015 to 2017. So we introduced, published the first paper in 2016 to generally introduce a concept of iterative approach. So right after that, we'll collaborate with our industry partner, IBA, to start a second phase of collaboration to address the urgent clinical needs through the simulation study, as well as we demonstrated the first time on the clinical system that the concept is not only looks great on paper, but also it can deliver compatible with the current clinical system, IBA ProteusOne. So this is a picture of Dr. Lee and I was standing together to hold the planning for the donorship ProteusOne plan, as well as the film symmetry, which irradiate during the dynamic delivery of the ProteusOne. And we published first paper in 2019 to show this concept is compatible with IBA ProteusOne. So now we're in the surface of the collaboration with IBA in the MakeIt Consortium Group. So we are going through the rapid engineer development and validation to prepare for the commercial release and clinical implementation. So now we just introduced a couple of recent technical breakthrough. And so the first one is we built the dynamic proton model, which is the first in the world. So it including the irradiation delivery sequence as well as mechanical model. As you see on this model, that we're able to achieve 2% on the irradiation model and 6% overall on the ProteusOne. So this platform is able to help the society moving forward and to implement the delivery sequence in the TPS as well as machine. So the next, with the establishment of the delivery sequence model, we're able to simulate whether the ProteusOne is efficient or not. So what we found that the ProteusOne is to reduce 58% of irradiation time, which is a significant improvement compared to the current clinical practice for RMPT. As you see on the right side of the picture with different disease sites, the ProteusOne is able to significantly improve the treatment efficiency in lung and head, neck, and brain patients, and also other cases as well. So the overall improvement, including the treatment setup time and also the patients walking through the treatment room. So the total reduction, as we see from these 2 days, we're around the 15 to 25% increase in our ProteusOne center. For the multi-room center, you probably can save more with the Proton module. So the next technical breakthrough is we're moving towards hypofractionation. As you know, people are looking at not only proton, but also photon. We are moving towards hypofractionation. So one challenge for proton is the robustness in terms of the geometry changes and also the motion mitigation. So the ProteusOne in these two papers will demonstrate that it's not only the plan quality is superior compared to the VMAT and RMPT, but also the ProteusOne is robust as VMAT in terms of geometry changes. As comparison, RMPT will have this huge issue when the geometry changes along the beam path. On the lung SBRT example, as you can see, the ProteusOne is able to mitigate the motion interplay effect compared to the RMPT. So here, we're going to show the general workflow, how the ProteusOne is going to work in the clinical settings.
So this is the first treatment planning on the ProteusOne to deliver on the IB proton machine. So this shows a partial arc to treat a donut-shaped target, represents the tumor surrounding the spinal cord, for example. So what we want to do is provide enough dose for this the ring structure while spare the middle of the mass here. So that's how the ProteusOne is able to do in reality. So that's what we show later on the QA and also film dosimetry using this treatment plan. So this is actually the first treatment ProteusOne plan generated on our treatment planning system for the delivery. As you see, we have a donut shape, like circular shape, and what we want to do is to spare the center of the mass here, just represents the tumor a tumor surrounding the spinal cord. So in this case, we use a partial arc to hit the target precisely while spare as much as the central mass as possible, like donut shape. So this is the plan. We transfer the IBM machine for treatment delivery.
Yeah, so one of the important things is how to quality assurance the product delivery. So this is a video show you that when the DynamicARC gantry is moving, the QA platform is rotated along the gantry as well to capture the dose precisely and reconstruct the dose offline. So after all the treatment planning and the QA process is done, now it's time to deliver the actual treatment plan on the Proton machine. So this is a real-time treatment record on the first delivery on the ProteusOne in the IBA ProteusOne.
Leo spoke to you about the generation of SpArc and the mechanics behind the delivery of SpArc. I'm going to talk to you about bringing SpArc into the clinic. The other term is DynamicARC. DynamicARC is sharper, more robust, simpler, and faster. In terms of being sharper, DynamicARC, when compared to standard 3-field IMPT for bilateral head and neck cancer, we did a dosimetric study and found a 30% reduction in bilateral carotid dose for SpArc compared to standard IMPT. So we saw a reduction in the moderate and low dose cloud with DynamicARC compared to IMPT. We also looked at DynamicARC in terms of high dose conformality. We did a dosimetric comparison for sinonasal cancers in which you are bound by critical structures surrounding your target volume, where we looked at dynamic arc versus standard three-field SFUD IMPT. And what we saw was not only a reduction in mean doses, but also high dose conformality. In other words, we saw reductions in max dose to the eyes, optic nerves, and brainstem. This is important for sinonasal cancer, in which you're often making the trade-off of target dose coverage versus critical structure dose limit. So with dynamic arc, you have the potential to increase target dose coverage while maintaining dose tolerances of the eyes, brainstem, and optic nerves. We also saw that dynamic arc is more robust. In this way, it reduces the interplay effect, which is simply when painting proton beam spots, you may miss a moving target. We looked at a comparison of dynamic arc versus standard IMPT for a locally advanced lung cancer case. We summed the individual 4D simulation slices along with a SpArc plan and a standard three-field IMPT. What we saw as the dose was propagated along those 4D slices, a more homogeneous dose distribution for dynamic arc versus IMPT with the potential for underdosing your target volume and overdosing with hotspots because of the interplay effect. So in other words, dynamic arc was more robust than standard three-field IMPT for a moving target such as locally advanced lung cancer. For breast cancer, we saw that SpArc not only can be more conformal, but also a more simple setup. Here, with a field size of about 24 to 25 centimeters, for a large breast patient, you may have to match medial to lateral fields to cover your entire target. However, with dynamic arc, because of your rotation and degrees of freedom, you're able to cover a larger volume in the medial to lateral position with a single isocenter. So not only is it more conformal, but it's a simpler setup because you only have to use one isocenter for that coverage medial to lateral. And most importantly, dynamic arc is faster. We monitored the treatment times for 1 day of the ProteusOne using IMPT, looking at lung, head, neck, brain, pelvic cancers, and other random cases we treated that day. So we not only saw that beam on time was faster with SpArc, but the actual treatment delivery from on and off table between SpArc and IMPT was faster. So what you can see is not only is dynamic arc more robust and sharper, but it's also faster in getting patients on and off the table, which can lead to more patients being treated in a single day. So in conclusion, as we showed you, SpArc in the clinic, or dynamic arc, is sharper, more robust, simpler, and faster.
Thank you for visiting Beaumont Proton Therapy Center. We're proud to show off our dedicated staff, innovative research, and state-of-the-art facility.